Alright, so new lesson, angular momentum. This is much easier than what it sounds like. It is literally the same concept as all the other angular quantities. So remember how linear momentum was was represented by a p, which it was equal to mass times velocity? Well, what's the angular version of m? It's inertia, and the angular version of v is angular velocity. So angular momentum is just, it's represented by L, that's the only difference, and it equals inertia times W. And that's basically the entire lesson for this section. Okay, so a woman is sitting on the spinning seat of a piano stool with her arms folded. Ignore any friction in the spinning stool. What happens to her angular velocity and angular momentum when she extends her arms outward? Okay, well, remember that angular momentum is equal to inertia times velocity, and inertia is mr squared. So angular momentum is mr squared times velocity. And also remember that angular momentum is always conserved. So if her arms extend outward, that means that her radius is getting bigger. That means her inertia overall is getting bigger, because since inertia is mr squared, and if r gets bigger, inertia gets bigger. So if angular momentum stays the same and your inertia gets bigger, that means that your w has to get smaller. So in theory, your angular velocity gets smaller if your radius gets bigger. So it slows down. And then your angular momentum, it's always conserved, so that's an easy answer. It'll stay the same. And now 19. A cloud of interstellar gas is rotating. Because the gravitational force pulls the gas particles together, the cloud shrinks, and under the right conditions, a star may ultimately be formed. Would the angular velocity of the star be less than, equal to, or greater than the angular velocity of the rotating gas? Okay, so what this is telling you is that the star, it got smaller, right? That means its radius got smaller. Inertia is mr squared. So if the r gets smaller, that means that the inertia gets smaller too. But since angular momentum is always conserved, and angular momentum is inertia, angular velocity, if the inertia gets smaller, that means that the angular velocity has to get faster. Has to get faster. So it's greater than it originally was. Okay, so two disks are rotating about the same axis. Disk A has a moment of inertia of 3.4 kilograms times meter squared and an angular velocity of 7.2 radians per second. Disk B is rotating with an angular velocity of negative 9.8 radians per second. The two disks are then linked together without the aid of any external torques, so that they rotate as a single unit with an angular velocity of negative 2.4 radians per second. The axis of rotation for this unit is the same as that for the separate disks. What is the moment of inertia of disk B? Okay, so first thing is write your values. So start with disk A. You know that the inertia is 3.4, that the initial angular velocity is 7.2, and that the final angular velocity is negative 2.4. And now disk B. You don't know the inertia because that's what it wants you to find, and you know that the initial angular velocity is negative 9.8, and that the final angular velocity is negative 2.4. The reason they're both negative 2.4 is because it says that they rotate as a single unit with an angular velocity of negative 2.4. Okay, so now we now we create an equation. Okay, so angular momentum will always be conserved. That means that inertia 1 W1 will always equal inertia 2 W2. Okay, that's important to know. So inertia of disk A times W1 of disk A plus inertia of disk B times W1 of disk B will equal the inertia of disk A times W2 plus the inertia of disk B multiplied by W2 of disk B. So now you just plug in those equations. The reason that works out is because it's the initial angular momentum will always equal the final angular momentum. So you plug in for the equations and you get that it will become 3.4 times 7.2 plus negative 9.8 times I, because you don't know what I is equal to 3.4 times negative 2.4 plus negative 2.4 times I, right? And now you just solve for I. So then you get that once you solve it a little bit, and then you just keep solving for I, and you get that I is 4.41 kilograms times meters squared for disk B. Okay, so when some stars use up their fuel, they undergo a catastrophic explosion called a supernova. This explosion blows much or all of the star's mass outward in the form of a rapidly expanding spherical shell. As a simple model of the supernova process, assume that the star is a solid sphere of radius r that is initially rotating at 2 revolutions per day. After the star explodes, find the angular velocity and revolutions per day of the expanding supernova shell when its radius is 4r. Assume that all of the star's original mass is contained in the shell. Okay, this may sound complicated, but it's actually really easy. Okay, so first thing, write down what you know. You know your angular velocity is 2 revolutions per day, and you know that your radius is just r. And you know that your final angular velocity is not known, and you know that your radius 2 is 4r. Okay, so then initial momentum is always equal to final momentum. So the initial would be this, and the final would be this. So you just plug in, you get 4r times W2 is equal to 2 times r. This 4r being r2, this W2 being W2, and this being the angular velocity and this being the initial radius. And then you just solve for W2 and you get 0.5 radians per second. Excuse me, not radians per second. It would be revolutions per day, because that's the unit that it was already using. And that's it. That's all you need to know for angular momentum.